everyone. Good afternoon. I'm Kai Young from Kent University. Today I'm gonna talk about a big research in last year. It's about water, CSH, magnetic field, and the improved concrete durability. Before everything, I have to talk about some research. Maybe everyone have heard about that. If you have a magnetic field, it may affect the morphology of calcium carbonate. Also, there's a lot of scientists put magnetic field into cementitious materials, and they found this kind of field may improve the durability of concrete structure, but their mechanism is not that convincing. They support their experiments by a lot of scenarios, such as the polarization of water molecules or nuclear spin isomers of water or water clusters or whatever else. And there's still a lot of scientists believe it is fake. So after giving a review of hundreds of these publications in recent decades, I think we can give our own hypothesis. Here, look, in our universe, maybe also in other universes, there's only two kinds of water molecules. One water, we call this para-water, because the two protons share totally different spin direction. And the other water molecule is called also water. The two protons have the same spin direction. These two water molecules are essentially two different materials. They have different physical and chemical properties, and only the also water will interact with actual magnetic field. Their ratio depends on temperature. At the room temperature, the ratio of para to also is 1:3. And they have different energy. They will form different hydrogen bonding network. And the para water will have 23% faster chemical reactivity in this chemical reaction. And the lifetime of these two kinds of water molecules are totally different. If you have a very high magnetic gradient, you can separate these two different molecules. Also, if you have a super high electric gradient, you can also separate them. So our hypothesis is, given a magnetic gradient, the two water molecules will interconversion because their energy level will mix, and this will lead into an interconversion of them. So what's the result? As you can see here, if you have a calcium in solution, the wave function of the whole collaterate can be resolved into a set of individual wave function of each water molecule. But if you give it a magnetic field, it's only one antisymmetric wave function can be used to characterize the whole collaterate. And the Borley principle will keep only the triplet state collaterate stable. In other words, in a super high magnetic gradient, the hydration radius of calcium will increase. On the left is the magnetic field in our lab, what we use in our experiment. The magnetic gradient is ranging from 500 to 1000 Tesla per meter. We can't test it, but we can simulate it. On the right is the distribution of the magnetic gradient and magnetic strength along this direction. The simulation is run on ANSYS and FEMM. So if magnetic field will affect ions hydration, what will it affect the CSH? As you can see here, in the formation of CSH, there are many processes involved. The first one is ions hydration, and then these hydrated ions will form pre-nuclearization clusters, and Then its flocculation. This flocculation is very important. As you can see in these figures, this is the turbidity during the formation of CSH. The flocculation happens in this stage, we call it stage 2. And in this stage, you can find a lot of CSH intermediate spheres like this. And then as densification, and finally, we will get a CSH in cement paste or concrete. The stability of the CSH PNC spheres is determined by the interaction force between them. So in other words, if we know magnetic field will affect ion hydration, this part is very difficult to test because we need very special equipment, but it has been proved to be true by a lot of scenarios and simulations. Now we are in this stage. We're gonna prove ion hydration will affect cement hydration or will affect CSH structure. So we have to calculate the force involved in these two CSH PNC spheres. As you can see here, there's a lot of methods to calculate these forces, such as the Monte Carlo, the MC, and BD or molecular dynamics or molecular mean field theory. So finally, we choose the molecular mean field theory because it's convenient, it's quick. Also, there's a lot of models based on molecular mean field theories, such as the very famous DLVO theory and the further modified DLVO theory and the very famous PB model. But if you're gonna use this theory in cementitious materials, most of the time you will get very ridiculous result. And then it's the PNP model, the BSK theory proposed by MIT and others like PNPF model. Here is the theory based on the BSK theory. They use it to calculate interaction force between two identical negatively charged layers. So how we involve magnetic field? If we have a thicker hydration shell, it means the electrostatic ion correlation lines, LC, will increase. And of course, the hydration layer will increase. And the cation's effective charge will decrease. And here we're going to talk about how we involve ion-ion correlation. In the BSK model, the LC is characterized by lines here, and we saw this fourth order PDE to get electrostatic potential with this boundary condition. And how we involve magnetic field, we relate LC to hydration radius, which has been used by many other researchers. Then we use this equation to quantify hydration potential. It is the second order PDE with this boundary condition. And magnetic field will affect these three parameters, LC, LH, and Q. As you can see here, this is a calcium ions in water. This is the first hydration layer, and this is the second hydration layer. We got this data from these publications, and it's very obvious that you can see here. If you increase the number of water molecules in the second layer, LH will increase, Q will decrease, and LC is related to two times of LH. And on the left is the force between two identical negatively charged layers. You can see if we increase the water molecules in the second hydration layer, the attraction force will increase. This is the model we used. And so we can see given a magnetic field, the attraction force between the CSH layer will be increased. But still, this scenario is not perfect because there's only 2 kinds of ions in per solution, and it's a 1D model, and there's a lot of improvement to be done. This is the MIT model, and if you check very detailed about these publications, you will find their method to calculate hydration potential is fundamentally wrong. So at present, we are using all of these scenarios and composed our own model. It's called 3D PMPF HCR model. At present, there's still some problem in our model, but still I can show you some results. If we put 2 negative charge layers in the simulation box, we can simulate a calcium distribution around the CSH layer. And our result about hydration potential and electrostatic potential are comparable with MIT's model. But still, if we go back to our problem, will it affect concrete durability? Everything we talk about up to now is about thermodynamics. And we have to say the final conclusion is also related to the kinetics. So our answer is the final effects is related, it depends to the competition between kinetics and thermodynamics. And now we can only give some useful information, which is that the magnetic field may affect the interaction force between CSH layer. So will it affect the concrete durability? There's still a lot of problems to be solved. So that's at the end. And we're gonna to thank a lot of professors and super nice researchers from MIT. And they really support me a lot during the pandemic and developed our series. Thank you. I think that's it.